Okay. So this I I I add this slide just for the sake of fun. You all know about the properties of solid, liquid, gas, fluid. But one thing should be remember that the solid can resist shear stress within the elastic limit, while the fluid undergoes continuous deformation flow under shear stress based on the viscosity under external shear stress. So fluid cannot resist the shear stress, while the solid can resist the shear stress within the elastic limit. So these are some basic properties I mentioned here just for the reminder. We know that the density of the water is about 1000 kilogram per meter cube or 1.94 slugs per foot cube. And we also know about the specific weight. The weight per unit volume of water is about 9810 Newton per meter cube and 62.4 pound per foot cube. The specific weight, the unit weight is basically equal to the rho g, and where g is the gravitational velocity. The specific gravity is based on the ratio of a fluid to the ratio of a fluid to uh, the, the fluid unit weight to the unit weight of a water. So basically, this dimensionless variable, the specific gravity, we calculate based on the unit weight of a fluid and the ratio of unit weight of a fluid to the ratio of the unit weight of water. So viscosity is also the important parameter of a fluid. This shows the resistance to any deformation or flow which under the applied shear stress. So the stress basically occur in between the different layers of a fluid when it flows through any type of a cross section, whether it is a channel or whether it is a pipe. So at the boundary condition, mostly the molecules shows the no slip condition, having zero velocity at the uh, boundary or the hard surface when the velocity or the molecules of a fluid touch the hard surface. So there it shows the no slip condition having zero velocity. So the viscosity is basically the ratio of the shear stress which usually occur between the two layers of a fluid to the deformation rate of deformation occurs due to that shear stress. So tau is the applied shear stress, while the dV by dy is the resulting rate of deformation. V is the magnitude of velocity, and distance from the y is the distance from the solid boundary. So you can see here that the y is the distance from the boundary condition. Dy is the just the differential part of that fluid, showing the deformation of dV by dy in the direction of flow. Mostly in ideal fluid, we took the dynamic viscosity of or the absolute viscosity of zero. A fluid will move when it's subject to shear stress, as I mentioned earlier. So most fluids have non-zero viscosity, so that no slip condition can be imposed. So here we are considering most of the in a water supply design is a water. We are taking it water for the water supply design. So if we consider some viscosity of that fluid, so taking the non-slip condition when it's come into the contact with the boundary or the hard surface of any type of structure, or whether it is the channel, whether it is the pipe. So here we are considering only will be a pipes. Therefore, at the boundary of a pipe, the velocity we will consider as a zero. Viscosity. So this is basically the absolute or a dynamic viscosity. So from using that, we can also calculate the kinematic viscosity, which is basically equal to the ratio of absolute viscosity to the density of a fluid. Elasticity is very important parameter in order to design any type of pipe, because the elasticity of varies from material to material. So if you want to design a water supply system, then you should know about the material, its elasticity, mostly in case of the hammering phenomena, the transient occurs. So the material most affect the whole process, the hammering process. So I will discuss that later. Mostly in the last lecture, the transient analysis, when we close the valve or when we shut down the pumps, so the effect occurs, or the suctions created, or the effect on the pressure on the material of a pipe, of the boundary of a pipe. So we will consider that, and we'll discuss in detail that how the elasticity affect the whole hammering process. So elasticity is basically the relates to the amount of deformation to pressure changes. So increasing is basically the ratio of change in the pressure to the change in the density of a fluid, or the ratio of the change in the pressure to the change in the rate of a volume. So here you can see that the increasing the pressure, the change in the volume occurs. So based on the change in volume, the density is also affected by increasing the or decreasing the pressure. For most application, we treat. So this is very important point. So if we design a water supply system in a water gym, so it treats the water as incompressible. But in hammering effect, when we design the walls, the pipes, or the pumps in water hammer, it's the other version of a water gym, where we analyze the water supply system for a transient analysis. So there, we assume that the water is compressible. So compressibility effects are important for large pressures due to the water hammer, or for very large speeds. So here we will consider, when we study about the water hammer, or using the, I will just try to give you a one lecture on water hammer as well when I get time, or when we lecture to deliver you the how the transient analysis affect the whole water supply system. Vapor pressure is also an important parameter. Basically, vapor pressure is the phenomena where is occurs by increasing the temperature of water, or by decreasing the pressure. Usually, when the fluid, just consider this a pipe, and here we have a wall. So when the fluid flow through this path, so the pressure at this point decreases compared to the upstream and downstream. When the pressure at this point decreases, it's the water bubbles created. Due to the creation of water bubbles, the bubble increasing number of molecules having high velocity, it bursts. So it greatly affect the pipe. So by increasing at a very high amount of velocity, or the increasing high amount of vapor pressure, may cause the bursting of a pipe. So these are the properties of a water at atmospheric pressure at the different temperatures. You can observe that how the density varies with respect to the temperature, and how the specific unit, the dynamic viscosity, and the vapor pressure effect increases as compared to the water is compared to temperature. So one point to remember, that if you design a water supply system, so the temperature of an area should be considered by taking these properties of a water in order to design the water supply system. Okay, basically, if we when we study the any system, we try to simplify system to in order to analyze easily. Similarly, in the case of fluid, when we analyze water flowing to the pipe or the channel, So we imagine that the fluid flowing through the pipe in a stream lines through in a lines that indicates the direction of a velocity at that point in any point when you draw the tangent to that point. So these are basically the streamlines showing the direction of a fluid, or in this case water. Streamline indicate the direction of flow and do not directly indicate the magnitude of the velocity. So basically, when we study um, the fluid effect, so the phenomena occurs in the pipe or in the open channel. So we consider these streamlines as a stream tube. The composition of these streamlines is called the stream tube. And also, when we study any type of a behavior of a fluid, we then consider a control volume, where we consider that some of water is going inside at that control volume and going outside from that volume. So based on this control volume, we derive different types of equations, and then we integrate over the whole system and get the different equations like the Bernoulli's equations, the continuity equations. So these are basically, first of all, we simplify the system by taking the streamlines, taking the stream tube, and by taking the system as a control volume, and then we derive different types of equations. So as we know that uh, the variations occur through the fluid, it may be steady or unsteady. Unsteady means that, for example, if we have a uniform channel or pipe and the fluids flowing through it. So if I consider this point, so at this point, after 1 minute or after 2 minutes or after 3 minutes, the velocity at that point will be same. So if the velocity changes at that point time to time, so that velocity or that flow will be called unsteady flow or velocity. Okay, similarly, in the case of uniform and non-uniform flow, uniform flow is that flow where the cross sections does not change. So before understanding the uniform and non-uniform flow, we should know about the 1D and 2D flow. In 2D flow basically occurs when the viscosity of a fluid is very high. Mainly in the case of honey, we can say that when it flow, so the velocity changes in the x direction as well, and the velocity changes in the y direction as well. So this type of flow is called 2D flow, when that the flow is only changing in the vertical direction, and uh, and same in the horizontal direction, that it is called 1D flow. In the vertical direction is changing because, as we know that due to no slip condition at the boundary of a pipe or of any structure, the velocity of your fluid is zero, while as we reaches to the center, the velocity of a fluid is increasing. So these are the 2D non-uniform flow, because the velocity is changing in the x and y direction as well, and by changing the cross section or the flow point to point is also changing. So that flow is called the 2D non-uniform flow. But when the flow is not just only changing in the y direction, so we approximate that the 1D uniform flow approximation. Similarly, in the case of open channel flow, this figure shows that how the velocity in the x and y direction is changes 2D non, showing the 2D non-uniform flow. And in this case, we are approximating it to the 1D uniform flow approximation. And in 1D, the uniform flow is also occurs if we consider this point, that at that point the velocity will be same, not changing, but as compared to section 2, it will be changing. So the section is changing at the section 1 and section 2, showing the non-uniform flow approximation. Okay, the fluid, let's have a discussion also at fluid statics to derive the hydraulic grade line equation. So hydrostatic fluid is basically those fluids showing having no acceleration and stagnant at one place or uniform motion. Normally, the pressure, normal compressive stresses for compressive stress force, for a compressive force acting on an area, we know about the equation. The force per unit area is the pressure. Okay, the gauge pressure is also important to consider in the water supply design. So the pressure that is expressed relatively to atmospheric pressure, which is taken as zero, is called the gauge pressures. Similarly, the absolute pressure is denoted. Absolute pressure is denoted by A or APS as a subscript. Is basically equal to the addition of a gauge pressure plus the atmospheric pressure. In absolute units, standard atmospheric pressure may be taken as 101.3 kilopascal absolute or 14.7. So the gauge pressure is usually when we measure the pressure at the junctions of a pipe. Mostly in a water supply system, we deal with the pipes and the junctions. So the pressure is measured at the junction is basically the gauge pressure. So just consider these two units, gauge pressure and absolute units, absolute pressure of PSIA. Um, the if we have a vacuum pressure of absolute pressure of 0, then we get the gauge pressure of minus 14.70. We know that the atmospheric pressure is 14.7 pound per square inch. If we have a value of absolute pressure 7.50, then we get just plug and chunk these values in this equation, you will get this type of a table. So to derive a hydraulic grade line equation or the hydraulic the head at any point, equation for any point. So consider a cube and took a small element of that fluid having a force or a pressure acting at that point, while the pressure or force acting at that point will be different from that because the pressure as we move downward increases. So at that point, the pressure will be less as compared to the pressure at that point. So as we know that the pressure is equal to the F by A. So the force exerting at that point will be equal to the PA. Similarly, the force acting at that point will be different from this point, so that there will be some change in pressure, and also the weight of a fluid is acting downward. So this equation derives just like that. That we also know about the unit weight of a fluid, which is equal to weight by volume, and volume is equal to area into the length of a fluid element. So by multiplying with the unit weight, we get the weight is equal to the unit weight into area into L. So by summing all of these equations, P into the change in area minus P plus change in area into the change in area minus the unit weight change in area, similarly change in the length. So the sign alpha is basically occur due to the forcing acting in this direction. So we have a theta here. So it's making the sign alpha or theta or alpha. So here at this axis, it forms the cos alpha, and this is axis is formed a sine alpha. So by solving this equation, we get this equation by subtracting this and by subtracting the uh, pressure, and similarly by taking common of area and divided at both sides, we get rid of area as well because the area is similar for all. And finally, we by just solving these equations, we get the hydraulic grade line equation. So this is basically the pressure head. Pressure head is equal to the gamma h. So the h is equal to P by gamma. And Z is showing the elevation head. So from this equation, you can identify that you can know that in the vertical direction, in the downward direction, as we go in any type of fluid, the pressure increases. In the vertical Z direction at the rate of minus gamma. Okay, so let's consider a reservoir having a fluid of unit weight gamma. So the weight at section 1 is atmospheric pressure, so the pressure at P1 will be equal to 0. And while at the point 2, it will be equal to gamma H2, and at point 3, it will be equal to gamma H3. So the pressure at any point from the below from the surface depend upon the height of that point from a surface. So increasing that height, it will cause increasing the pressure. Okay, in different type of elements, different type of structures, consider these type of structures just like storage tanks, different type of storage tanks. So at the point at the same elevation will have same pressure, whether it is belong to different type of structures, but the pressures at C will be equal to pressure at D, and similarly pressure at E will be equal to pressure at F. But it is for those which have same for structure having same fluid, but having a fluid of different densities, the pressure at C will not be equal to pressure at D. Let's solve an example. Consider two fluids, oil of specific gravity of 0.65 and water below of it. So the pressure at 1 will be equal to 0 because of atmospheric pressure, while the pressure at point 2 will be equal to the specific gravity multiplied with the unit weight. As you know that the specific gravity is equal to the unit weight of fluid and the unit weight of water. So if we multiply unit weight of water, we get the unit weight of fluid. So the unit weight of water is 9,810. By multiplying the height of that fluid, we get the pressure at point 2. Similarly, we know the pressure at point 2, so we can get the pressure at point 3 as well by subtracting the 1.2 minus 0.4. So we get this distance. So we get find the pressure at 3, and similarly a pressure at 4 as well. So to the basic philosophy behind the design of water supply system is basically based on the continuity equation, the energy equation, and the momentum equation. So first of all, we will discuss the continuity equation. So as we now consider just a portion of a pipe where the velocity is where the flow is enter into the pipe at one side and going outside the pipe at the other side. So the continuity equation shows that the inflow of a fluid, inflow will be equal to the outflow, and the storage, if any, occurs in that fluid, will be the time rate of the storage will be equal to the sum of inflow and the sum of outflow. So usually, as I mentioned earlier, that usually when we study about any type of a fluid or any type of phenomena to derive some types of equations, so we consider a control volume. So we are considering here a control volume where water is entering or the fluid is entering at one side and leaving the that control volume at the other side. So this is the continuity equations which we'll be using for the finding the diameters of a pipe, the velocity or the velocity in the pipe and other stuff. So considering an example having a reservoir of a channel having a height of 4 meter, width of 6 meter, connected to the 1 meter of diameter, Similarly, and also connect to the pipe of about 0.5 meter diameter of pipe. So as we, according to the continuity equation, that the flow at that point will be equal to the flow at that point, the three section, by considering the three sections. So the flow at section 1 will be equal to the flow at section 2, and the flow at section 2 will be equal to the flow of at section 3. So basically, when the fluid flow through all these sections, the areas varies. So the areas, as the areas varies, the velocity also changes. So just by checking the various of these cross-sectional areas of these structures of pipes and the reservoir or open channel, we get this equation. So we just consider it is as equation 1. Now based on the other equation, so based on the energy equation, we will derive the energy equation for this example as well. So as we know about the Bernoulli equation, for steady incompressible flow in a closed pipe system or open channel, the pressure head plus the velocity head plus the Z, the elevation head plus the head given by a pump will be equal to the pressure head at point 2, the velocity head plus the elevation head plus the head given or the head utilized by the turbine, plus the head loss occurs when the flow through to the pipes. So mostly the head losses occurs when it flows is to the when the fluid flows through the pipe, mostly due to the friction between the fluid and the pipe. So HP is basically the energy head provided by a pump is equal to the efficiency of that pump, the power input given to that pump divided by the flow and the product of flow and the unit weight. And HT is basically the energy head removed by a turbine. So turbine basically utilizes the head created by any system when we install the turbine at the downstream side. So it produces the electricity or other stuff like that. Similar, or the HL, basically the head loss is the sum of all fraction or minor losses as water moves from section 1 to section 2. Kinetic energy factor, it is basically varies from material to material, or the when it's the valves occurs in between the flow or the pumps, so that varies accordingly to that. So consider an example as I show here. Just create a Bernoulli's equation for that. So always to solve any type of equation, any type of problem, in case of a fluid or driving an energy grade line or the hydraulic grade line, we should first consider assume a datum for that. If you didn't assume a datum for that, then it is useless to define anything. So first we will consider or assume a datum for that, and considering that some point in a system have a elevation of Z1 and want to have elevation head of Z2. So from that we can shows or write equation that the pressure head at point 1 plus the elevation head plus the velocity head will be equal to the pressure head plus the plus elevation head plus the velocity head plus having the head loss occur through that pipe at the downstream side. So by using the Bernoulli's equation, so as we know that at that point the pressure head is 0, so we will just consider that at 0 due to the 0 atmospheric pressure, and we know that by considering the bottom of that river or the reservoir as a datum, so the elevation head of this the surface of a water will be equal to the 4, and we don't know about the velocity head because we didn't derive that. We will just derive that by plug and check in the momentum equation. Then we can get the velocity of v1, v2 and v3. So we also don't know about the pressure head at section 2 at the diameter of 1 meter per circular pipe section, and this is basically the equation at the section 3. So we get these two equations from the continuity equations and the Bernoulli's equation. Similarly, we have also another equations, momentum equation, which basically derive from the just considering a pipe where the flow enter into the pipe and flow going outside of the pipe. So for momentum equation, we consider that the mass flow rate is equal, the inflow mass flow rate is equal to the outflow mass rate. So as we know about the mass, that the density equation is equal to the mass per unit volume. So by putting the equation of M into this equation, we get that the rho V is equal to by T, and we know that the V by T is a Q, flow rate per time, volumetric change of any volume change per unit time. So we get that this is basically the mass flow rate occurring through this cross section of control volume. And to find the force, basically we are going to find that how much force will be required. Wait for a while. Okay, so to find a force acting by or exerting by this plate on the fluid at that side, we have to find the force is acting by the plate on the water at the reservoir or the channel to retain on this side. So we are considering this section 1 and 2, where the mass of a fluid is acting in the direction having a force of F1 and the force of F2 in this direction. So to find the FP, the force exacting by the plate on the reservoir or the retain the water at that side, first we have to find the this first we have to find this pressure head at this point, because we require the pressure P2. So to find that, first we have to find the velocity 1, V2 and V3. To find V1, V2 and V3, just move these coefficients to that side to get the equation of V2 in terms of V1, and similarly for the equation of V3 in terms of V1, and plug and check in these equations. So we can get the velocity V1, V2, V3, and when we put these values in this equation, we can get the pressure head. And by knowing the pressure head, we can then put in these equations to find the F2, F1, and then we can easily find by putting these values in this equation to find the pressure exerting by the plate at the reservoir. So the total head at any point when the fluid flowing from one to the other point is equal to the pressure head plus the velocity head plus the elevation head. नरशाद भाई, ये टाइम आउट हो रहा है तो रिकॉर्डिंग स्टॉप करके दोबारा शुरू कर लूं?
Yes, now you should stop this session and share the next
Okay,
link.
I'm going to create another meeting room.
Okay.